Welcome to the course Business Analytics and Data Mining Modeling using R. So in previous few lectures we have been discussing artificial neural networks, and in particular in previous lecture we started our modeling exercise using this small data set related to G samples and their acceptance or rejection based on two predictors, FIDE score and shortlist score. So we were at this point, so we were trying to build this model. So let's start again. So data frame we had already created in the previous lecture. So the same data frame that you can see we are going to use data frame 6 observations, 3 variables. The particular neural network architecture that we are going to use is the same that we had used in previous lectures. This is the so the architecture is this one. So this was the architecture that we had used in previous lectures for this particular example, right? So these are the connections, and then further, and then bias values. So we can see these connections and bias values. So this is the architecture that we are going to use. So as I talked about, we can certainly do certain experimentation with this particular architecture. We can certainly add more hidden layers. So we can have one more hidden layer here with 2 nodes. So this kind of experimentation we can always perform. However, what has been seen that typically one hidden layer is sufficient to model even the most complicated complex relationships. So we typically start with one hidden layer, and typically the performance is higher for the one hidden layer networks. Again, in terms of how many nodes that we should be using in a particular hidden layer, that is also, of course, we can experiment with that part also. So we can of course have one more node, and that experimentation and the performance of that particular network we can always compare it with. So we can always build different candidate network model, and we can always check which one is performing better, and those kind of experimentation with the network architecture can also be performed. However, for this illustration, for this exercise, we are sticking to this particular network: 2 nodes, 3 nodes, and 1 node in the input layer, hidden layer, and output layer respectively. So let's discuss further about this. So the package, as we talked about, is the neural net, and the function is neural net that we are going to use to build our neural network model. So the first argument is the formula for the model equation. As you can see, acceptance is the output variable, outcome variable. Then we have 2 predictors, FIDE score and shortlist score. And then data is coming from this data frame df, and you can see the next argument is hidden. So that is the number of hidden layers, and that is the number of nodes in different hidden layers. So we have just one hidden layer, and we have 3 nodes. So we have just mentioned 3 here. However, if we have more number of hidden layers and different number of nodes there, so that can be specified using this particular vector. Then we have start weights. So this is for the initialization. So like we did in our previous exercise with the same data set, so we can see we need 13 values. So this we can understand. We have number of bias values 4. So we have 4 bias values, and here for every node we have, it is connected with the nodes of next layer. So 3 into 2, 6 plus 3. So we have 9 connections, and we have 4 bias values. So in total we need 13 initialization, 13 values we need to initialize. So the same thing is mentioned here in the start weights. So you can see start weights run if 13 values, and as we talked about that typically we initialize these values from -0.5 to 0.5. So the same thing is mentioned here. So this will be used, these particular values are going to be used for the initialization step. And then when we see another argument reps, that is for number of repetition that we want to, number of times that we want to train our model. right. So we just want to run it once, right. So if you are interested in finding more detail about this particular function, you can go here in the help section, neural net, and you will get more details about this particular function. You can see all these arguments, and for example, specifically we were discussing a rep. So you can see number of repetitions for the neural networks training. So in this case we just want 1. If you specify more than 1, then of course you will have in a way you will have 2 candidate models that so that are actually based on 2 runs. So in every run the results might change slightly, as we have been talking about that machine learning algorithms or data driven models, they are sensitive to data. So therefore every run results might change. So from those runs we can always select the best model. However, in this particular case, for the illustration, we are just running building our model just once. Now the algorithm that we can select, so there are multiple options here, so that we can you can see in the help section. So this particular argument algorithm is here. You can see many options here. So we have backprop, that is traditional backpropagation algorithm. Then we have rprop plus, rprop minus, and other variants. So all these could be used to build our neural network model. However, for our exercise we are using backprop. Then certain arguments in this particular function depend on the algorithm that is being used. So for example, in this case backprop, we might specify one more argument, that is learning rate, right. So we discussed about the learning rate, that the value, the constant value that could be used for the to control the amount of learning that happens in that happens from previous iteration or in each iteration. So this is 0.1. So right. So whatever formula that we saw, the updation formulas that we saw in the previous lecture for thetas and weights, so there it was, the values were the addition was the learning rate into the error value. So you can see 10% of that particular value is being used to learn. Now we have error.fct. So this function again can be used. So this is SSE. So this can be used to check the overall model error. Then we have act.fct. So this is activation function, which is nothing but what we have been calling as transfer function. So this activation function is actually the transfer function. So as we talked about different alternatives, so logistic is the most popular, so that is being used here. Then as we talked about in previous lecture, linear output is the argument that is to be specified as false if we are building a classification model, and if we are building a prediction model, then this has to be specified as true. So let's run this code. Let's run this and we'll have our model. Now in the model we many values are returned. So one of them is result.matrix, that will actually have the values of bias values and connection weights, and few more parameters about the model. So you can see here we are just looking at first 3 values. So first 3 values of this particular matrix, so and first column. So you can see, so first 3 values are actually about error. So this error is actually based on, so this is actually SSE value because we had used SSE here. So we have other options also for model error. So as you can see here, SSE and CE in the help section, and you can see CE is cross entropy error and SSE is sum of square error. So these are the options that could be used. Then we have reached this threshold, so that is 0.0098. So that is about 0.01. So threshold we had not specified. However, the default value for threshold is there, so that we can see, you can see threshold is 0.01. So the threshold has reached to this level, so therefore the training process was stopped, right. So the threshold is again based on the error value that we talked about, and the steps that have been taken, 6 steps were required. However, if as we talked about, if the model is not able to converge, then probably the training process would be stopped by the limit that is specified in the number of steps. However, by default this limit is quite high, so therefore there is good chance that model will converge. You can see the default value is step max in the help section. You can see step max it is 1 e plus 0.5, so that is 10,000 I think that is 10,000 steps, more than so that is more than 10,000 steps, 1 lakh steps, so that could be used. So those number of steps put the limit. So in this particular case only 6 steps have been used. Now let's move forward. So next thing that we would like to understand is the interlayer connection weights, so which is nothing but the information about these values. So these are some of the weights. So we would like to see from the model, the final model that we have, what are these values, so thetas and weights. So first we'll look at these values and these weights and theta combination, and then here these values. So typically because we have one hidden layer, if we had more hidden layers, then again we can. So for every interlayer combination, so input layer to first hidden layer, in this case we have just one hidden layer. So from input layer to this hidden layer we'll have few weights and bias values. Now next is from hidden layer to output layer. So again we have some weights and bias value. So if we had more hidden layers, so we would have more such combinations. So interlayer connections, weights and bias values, we want to have a look. So first we'll look at the input layer to hidden layer connection. So this is the matrix that we can, this is actually a list that is returned when the model is built. So mod $weights. So within this you can see in the list, the first element of this list is actually nothing but a matrix for storing these weights, right. So by default these values are stored using the default row number and column number 1, 2, 3. However, I have changed the dimension names, that is row names and column names for this particular matrix, so that we are able to understand which particular value is for which particular connection or bias or for which bias value for which particular node. So we so this is the code. So you can see I am using dim names function, and we so this function allows us to change the row names and column names of a particular matrix or data frame. So in this case we can see the list is to be supplied. So for list, first element is always the row names, and then the second element is the for the column names. So let's execute this code, and you can see this is the result. You can see bias values for node 3 is this one, node 4 is this one. So you can see for node 5, similarly a node 1, so which is also corresponding to the predictor fat. So the connection weights are specified. So from node 1 to node 3 and node 4 and node 5, these are the weights. Then node 2, that is corresponding to the predicted salt, and the connections to node 3, node 4 and node 5, and the connection weights we can see here. So specific connection weights and their values, the bias values and connection weights values we can access in this fashion. Similarly from hidden layer to output layer also we have 3 weights and 1 bias value, so 4 values. So that also we can access in the similar fashion. So again I am changing the dimension name here again for this particular second element of weights list. So again as you can see, bias the list is being supplied with first element being the row names and the second element being the column names. So let's execute this code, Now you would see that the row names bias. Now you see the row names have changed. Now the hidden layer bias and hidden layer bias value and nodes, they have become the row names, and the output layer nodes node has become the column name. So you can see bias, that bias value for this particular output node, and then we have this connection weight from node 3 to node 6, then node 4 to node 6, and node 5 to node 6. So these are the connection weights and bias values for the model that we have just built. Now the final output values, the values that we get from the output node. So this value is also returned by the model, by the function in our model object. So this can be accessed using net dot result list. So mod dollar net dot result will give us these cold values. So in this particular case we had just one node, so we have just one value here. So because this was for classification, this was classification task. So these values can be compared with the with our cutoff value. So in this particular case we are taking 0.5 as the cutoff value, which is equivalent to the most probable class method, where if there are only two classes, then 0.5 cutoff value will actually implement that most probable class method. So we will get the specific values using these scores. So if you want to have a look at the scores also, so we can look at the scores as well. So if we run this, you can see this is a list, and we have just one node and 6 observations there. So these are the scores. So if we compare this with 0.5, we will get the values. Let's unname these column names, these names, dimension names, and we'll get this. Now we are creating a table with the scored the predicted class, and then actual class, and then the predicted value, that is the we can say the probability scores, and then predictors. So this is our data frame with all the information, the relevant information. Predicted class, you can see all the observations have been predicted as class 1, belonging to class 1. And if we look at the predicted values, all of them are more than 0.5. So because this was a small sample, just 6 observations, you can see that all the values have been classified as belonging to one particular class. And you can see the predictors also, their values also. So now we can look at the performance. However, this is quite obvious, 3 cases correctly classified. So in this case, as you can see, the predicted class is all the observation have been classified as class 1. So therefore we need to make certain changes in this particular code that we have been using in other techniques, because there won't be any values for label 0. So therefore we need to specify that explicitly, so that actually comes in the classification matrix that we want to generate here. So you can see that mod train C, I am converting it into a factor variable and then giving these 2 labels, so that even if there are no observations being predicted as belonging to class 0, still that particular column in the classification matrix would be displayed. So let's run this. So you can see this column I was talking about, so no observation, but it is being displayed because of this change in the code that we have done. If we had used just the mod train C directly, this column would have gone. So we can see that 3 values in the diagonal element 3 observation have been correctly classified, and 3 observations are incorrectly classified. So all the observations belonging to class 0 have been incorrectly classified as class 1. So the classification accuracy and error are also obvious, 0.5 in this case. We want to have a look at the network diagram using R. So this is the function plot, and we have to pass this neural network object mod here, and we will get the diagram. So you can see here. So you can see here that this is the neural network diagram that has been prepared by this function plot. So you can see fat score, salt score, these are the two predictors corresponding nodes you can see here, and from each node you can see the values, the weights from both these nodes, and you can see the bias values also here. So 3 bias values corresponding to 3 hidden layer nodes here, and then we have 1 bias node for the output node and 3 connection weights for the output node, and then we have the so this particular output node is corresponding to the acceptance that is our outcome variable. So other details, as you can see, this was the error that is the SSE value and the number of steps that were required to reach the conversion, right, to stop the network learning process. So this is our model. Now so this example was we used a small sample, just 6 observations. So probably this was not an appropriate example, an appropriate sample for us to understand build a good enough neural network model. So what we'll do, we'll use our used cars data set that we have been using in other techniques as well. So this particular data set we are going to use to build a model with a slightly larger sample size. So because we would be importing data from Excel file, so let's load this package library. Now let's import this file, used cars. So you can see 79 observations of 11 variables. However, even for this data set is also small, but better than the previous example that we have used. So let's remove any columns, any rows. Let's look at the first 6 observations. So these are the variables we are already familiar with this data set. Brand, so this is about the used car. So we would like to build a prediction model to predict the value offered price value of a used car. So the variables that we have: brand, model, manufacturing year, fuel type, it is petrol, diesel or CNG. Then we have SR price, that is showroom price, that is the price when the that particular used car was first purchased. Then we have kilometers, the accumulated kilometers. Then price, the offered price of the used car in the current condition, that is that we can see through the different variables. Transmission 0 or 1, that is manual or automatic. Then the owner's previous number of persons who have actually owned this car before this sale offer, so that is there. Then the number of airbags, and then we have another variable C underscore price. However, we won't be using this particular variable C underscore price. Now from the manufacturing year, as we have been doing in other techniques also, when we use this particular data set, that we compute the age variable, so that is more appropriate for our prediction model. So let's compute this, let's add it to data frame, and let's also take a backup of this data frame. Now if we look at the variables, now we would like to get rid of certain columns, certain variables. For example, one is I think brand name. Yes, so brand name, model name and manufacturing year are no longer required. And the last one, that is as you can see, this is actually C price we don't want. So this is actually, we have 12 variables. This is the variable number 11. So we don't want this one as well. So because we are going to build a prediction model, so let's get rid of these columns. And now let's look at the variables that we have. So we have now 79 observation, 8 variables. So these are the variables of interest to us. Now what we'll do, as we discussed in previous lectures, that the neural network models perform much better when we have the scale of 0 to 1. So if all the variables they are in this scale 0 to 1, then probably neural network model, they converge quickly, and also the performance improves. So in this particular data frame, as we can see, we have two categorical variable, fuel type and transmission. So however, as we will see that neural network, as we did in the previous exercise also, the acceptance was categorical outcome variable, but we did not change it into a factor variable, because the neural network function, it doesn't allow us to do that conversion. So all the computations are done internally in that particular function. So we would be required to change some of these variables. What we will do, so this is one particular example in our environment where we have to explicitly create dummy variables. So dummy coding we have to do probably for the first time. So we have been gone through so many techniques. So typically we convert the variables into factor variable, and the functions take care of the dummy conversion process and the model building later on. However, in this particular case, we will have to explicitly do this. So fuel type, we have 3 labels. So let's check the labels: CNG, diesel, and petrol. So all these labels will look to convert them into dummy variables. So this is one way to achieve that. You can see. So CNG, if DF1 $, fuel type, if it is CNG, then because this logical operator we are using, so therefore if it is CNG, then it will be true, otherwise false. So it would be a logical variable. You can see in the environment section, CNG has been created, logical, you can see false, false, true. So in the neural network function, the values should be either the variables that we use, either they should be either logical or numerical. So we are converting the factor variables, the categorical variable, into logical variables, the logical dummy variables. So now let's convert diesel and then petrol. Then we have another variable, transmission, that is also factor variable. So let's convert it into a logical dummy variables. So manual T and auto T. However, as we understand that we won't be using all categories, and one will be taken as the reference. So we would be for fuel type we would be taking only 2 of the dummy variables in the modeling exercise, and for transmission also just one of the dummy code in the modeling exercise. So we will take diesel and petrol, these 2 categories of fuel type, and the automatic transmission as the one category from transmission variable. So next process, as we talked about, as we discussed in previous lecture, is we need to convert our numeric variable into bring them into a 0-1 scale. So this is how we can do it. So what first computation is, we are trying to compute the max values for all the numeric variables. So you can see DF1 data frame, we have excluded column number 1 and 5, which are the corresponding to fuel type and transmission. So we are left with only numeric variables here, and then we are trying to compute max value for all these variables, and then in the next line we are trying to compute the min value for all these numeric variables. So let's execute these 2 lines, and you would see that in max DF1 here in the environment section we have 6 values, because we have 6 numeric variable, and again min DF1 6 values because we have 6 numeric variables. So the max and min values have been computed. Now we can use these values in the scale function. So this scale function we are going to use to normalize to 0-1 scale. So you can see center is now min DF1 and the scale is max DF1 minus min DF1. So the particular formulation that we discussed in the slides, so that is how it can be done using R. So scale function can be used, and then we will store these values in the same columns. So let's execute this code. Now so we have scaled all these, we have normalized all these numeric variables. So let's add the dummy variables and create a new data frame that we are going to use in our modeling exercise. So diesel, petrol, and automatic transmission. So this was these are the variables that we are taking into our modeling exercise. So let's create this data frame. Let's look at the structure of this final frame. So this is the frame DF2, that data frame that we are going to use for our neural network model. So you can see we have variable SR, price, KM, price, owners, airbag, and age, all have been scaled to 0 and 1, and you can see the values there in the structure output. And then we have 3 dummy variables which are being taken as the logical variables here: digital, patrol, and automatic transmission. So once this is done, we can go ahead and do our partitioning. So df2 is our data set now. So we'll take 90% of the values in the training partition, and the remaining 10% of the values will be left for validation testing partition. So let's create this. So let's create training partition, then test partition. Now the same function, same package, a neural net that we are going to use here. So neural network structure that we have to decide right now. If we look at the number of variables that we have, so we have 9 variables. So one of them is the outcome variable, that is price. So that leaves us with 8 variables. So that is, we have 8 predictors. So therefore in the input layer, as we have been doing for previous examples, so corresponding to 8 predictors, we would like to have 8 nodes. So that would cover nodes number 1 to 8. Then hidden layer, as we talked about, that typically one hidden layer is sufficient to even model the complex relationships. So we will take just one hidden layer, and we'll take we'll have 9 nodes, so one more than the number of predictors here. So we had 8 predictors. Well, let's take 9 nodes. So of course we can do experimentation with the number of nodes and even with the number of hidden layers. So that will cover us the nodes number 9 to 17. Then we'll have just one node in the output layer, that is node number 18. So with this network structure, we can go ahead and we can build our model and see the performance. Of course, after experimentation, we can try out different candidate models as well, and then finally select one. So we'll stop here, and we'll continue model building exercise for this particular data set in the next lecture. Thank you.